Action.
We are Team 10 with the Wirtz Pump Project. My name is Isaiah Finney.
My name is Michael Jodat.
I'm Aaron Matejcik. So with the Wirtz pump, we were examining fluid dynamics, and we created a spiral pump that resulted in the positive pressure differential, which presented with a vertical transformation of water. With these images here, we are looking at our actual assembled pump. Essentially, water gets scooped up out of the basin, goes around a bunch of circles, and then exits through the main axis there, all rotating on these bearings.
This is a theoretical model for the Wirtz pump. So basically, the main controlling variable for the Wirtz pump is the angle phi, which is the angle that the water plug makes with respect to the center of the circle. The operation of the pump is based off of these alternations between water and air plugs, which results in a summation of pressure that is greater than the input pressure at the output of the device. This table below contains all of the parameters for the physical construction of the Wirtz pump and was used to calculate the theoretical output pressure and mass flow rate, which were found to be 17.13 psi and 0.07373 pound mass per second, respectively. For the mass flow rate calculation, we use the same assumptions as before, and using the knowledge that the pump was submerged a total of 1.5 inches, we found that phi was approximately 0.7565. Using phi along with the cross-sectional area and the outermost radius of the pump, we calculated, as stated before, that the mass flow rate was 0.07373 pounds per minute at an angular speed of 75 RPMs.
The team had to make some key adjustments to further stabilize the pump. 2 horizontal braces were affixed to the front and the back. The purpose of these 2 braces were to aid in the rigidity of the pedestal itself, in addition to correct the wheel alignment. This was done so that the wheel remains perpendicular to the water's surface and it operates as it should. The team also made some minor adjustments, such as realigning the axle to the pedestal once the new braces were installed, and fixing minor leaks near the stepper motor axle assembly. The team also quickly discovered that the original measuring device was producing inaccurate results due to a combination of fluids at work. The solution was to essentially create a U-tube manometer so that the team could accurately measure the water column height, which was our Z value.
And here's a demonstration of our pump in action. For the next step, what we did was we took the data that we've collected. In this case, we started off by collecting the water discharged from the pump itself, and we averaged that over the course of several minutes. By using the density of water, we determined that the mass flow rate was 0.0208 pounds mass per second. After calculating this, we then used the mass flow equation to solve for the average velocity throughout the system, which we found as 0.2445 feet per second. Once the average velocity was found, we then used this information to collect the volumetric flow rate. For this, we had found the volumetric flow rate to be 0.000334 feet cubed per second. And then to round out the equations or round out the calculations, we needed to calculate our loss. With the loss, we started off by finding the Reynolds number. The Reynolds number we calculated as going to be 679.5. So because of this, we were able to determine that the flow was laminar, and we were able to use a standard friction equation without going into Churchill's or anything fun like that. So with our friction factor, what we found out was we had a friction factor of 0.09411. Then we moved on to calculate our minor losses. Through the minor losses, we noted that we had a couple different factors that contributed to our losses. So with that, we found that there were 2 sharp edge pipe exits that went from the spiral into the axis. And we also had a 90-degree miter bend at the rotor union. We also, which had veins on it. And then we also had a 90-degree that went, that contributed to our vertical, or that changed our flow from horizontal to vertical for our measuring. With all this information, or all these taken into account, we did calculate that a head loss was a total of 0.1118 feet.
As stated before, our Reynolds number was less than 2300, which means it's laminar flow. The friction factor was 0.09411. The head loss was 0.1118 feet. So using this information, we were able to calculate the necessary thermodynamic values that we were trying to obtain in this project. So to start off, first, the mass flow rate, the theoretical was 0.07373 pound mass per second. From the measurement, we found that the actual mass flow rate was 0.0282 pound mass per second with an error of 71.8%. The cause of this large error was most likely due to the fact that we were operating at lower than optimum angular speeds, which resulted in a discontinuous flow rate. Pressure output, the theoretical pressure was 17.13 psi, whereas the actual pressure was 15.6 psi with an error of 8.93% between the two. For the efficiency, we used the previously stated friction factor and head loss to calculate the pump power output, which was found to be 7.453 times 10 to the negative 5 horsepower. And for the input power, we multiplied the voltage and the current that was inputted into the stepper motor, which were 1 amps and 11.1 volts, which equated to 11.1 watts or 0.01489 horsepower. Using these two values for the power output and power input, we calculated and found that the efficiency of the pump was 0.5%. This low efficiency could be due to the low angular velocity and the discontinuous flow, as well as increased friction in key areas along the frame and shaft of the pump.
Some recommendations and improvements. We would like to improve the motor power combination to better handle the additional mass of the water itself. Hopefully get that angular speed going a little faster. Would have it like to increase the size and also pay greater attention to the loss reduction so we can increase efficiency.
All right, and then that sums up our project. Thank you so much for watching.